Hello, hello. How are we all doing today? Isn't it a great Thursday? Let's see. Oh, good morning, Lord Melbury. Well, I guess it's afternoon for you. 10 degrees C in the UK today. About 20 here. Going to get up to about 32, which is really warm for this time of year. Guess that would be about, what is it? It's about 20 here, so about 68 to 69 degrees. Going to get up to about 90. Time to break out my short sleeve shirts. Hang on, just getting my computer set up. Well, I've reminded you a couple of times over the past few days that next week there will be no sessions. It's our Easter break. We get a week off from classes. And then so we'll be back on, what does that make it, the 19th, I think? If I got my dates correct. Or 20th, somewhere in there. So all next week, no classes, no sessions, and then we'll be returning the week after that. Usual time. Okay, let's see. Today, we are learning about how we can speed up the password cracking process by pre-hashing all of the passwords. So load the passwords into memory, hash them all up front, and then we can do an easy search to find the hash that we're looking for, and then just simply look right next to it, and there will be the password. So if you recall last time when we left off, we had learned how to load a text file into the computer's memory and set it up so that we had easy access to all of the elements of that array of strings, if you will. So it looked something like this. We had this array, and in that we had some words like pizza, and then a new line character, and then a new line character, and then maybe fruit, what else? Burgers, and so forth. And then we went through that large string. We used dynamic memory. We used the malloc function in order to allocate all of the memory for that file, pulled it in all at once using the fread function, and then we went through that large string, replaced all of the new line characters with nulls. So we replaced that with a null, that one with a null, that one with a null, that one with a null. And that essentially breaks up each one of the strings into individual strings. It breaks up the larger string into individual strings. And along the way, we were able to count how many entries we have. Just count the number of new line replacements we did. That'll tell us the number of entries that are in the file. And that allowed us to build a new array, a second array. And each one of the elements of that array points to the first character of each one of those strings. The question is, why should we split it into an array of strings like that? We have to iterate through the whole file anyways. So you're right, actually, for we are going to need to just go through this one word at a time anyway. So we could just simply kind of like go through the file and look at each string individually. But the reason why I'm showing this to you is because what we're leading up towards is not only splitting up that file into individual strings, but then doing reorganizing the strings to make it faster to search. So we're going to have to be able to shuffle them up, to move their positions around in order to make a search more efficient. We're actually going to sort them at some point. But we're going to do that not this week, but when we come back next week. So that's why we're breaking it up, so that we can shift their positions around. And also, if we're cracking a whole bunch of passwords, we're going to want to do several passes through that array of strings. Not just one pass, but several passes. So breaking them up into individual strings will just make it easier to index into each one of the strings as we go. Okay, so we've got this array of pointers, and each one of those pointers goes to one of those individual strings. And now we can very easily crack a hash by just simply iterating through that array and then hash each one of the words and then see if it matches our target. And I think is that where we left off last time? No, where we left off last time was just simply loading the, oh yeah, here we go. We can search for a target. So let's just review the code here. So the first thing we do is check the number of command line arguments, make sure that we provided at least one file name on the command line. Then we use the stat function right here to get information about the file. And the one thing we're interested in mostly is the size of the file, which we get from the st_size field of the stat structure. Once we have the file size, we're able to use malloc and just allocate that much memory for the file. Then we open the file, use fread to pull in the entire file all at once. So we tell it to read into the contents array, which was the string returned by malloc, pull in the entire file from file f, which is our list of words, and then simply close the file. Next, go through the large array, find every instance of a new line, and replace it with a null character. And along the way, count how many times we did that. That'll tell us how many entries are in that file. Once we've done that, we can allocate more space, a second array, for this array of pointers. We know how many entries are going to be in there, and then each one of those entries is going to be a character pointer. So we allocate space for that number of entries, character pointers, and what we get back is a pointer to that array. So we get back a character pointer, and that points to this new array that we've just allocated. And then finally, we go through that array. We assign the first entry of the array to the first entry of the file. And then we go through the rest of the file, starting at character number 1. And then every time we find a null character, we store away a pointer to the next entry, the next character in that file. And we also go to one less than the length of the file because we don't want to do that to the very last entry in the file. The very last entry in the file doesn't have an entry following it, so we stop one character before the end so that we don't look at that very last character. And then finally, we can do a search. We can search through that array very easily. We just index into the array like it was any other array, and we can do string comparison functions on it. So setting up this data structure like I've shown here is in fact very similar to the way the shell handles command line arguments. It takes your entire command line, it breaks it up on the spaces. So wherever it sees a space, it essentially inserts a null character to truncate each word into individual strings, and then it builds up this array that points to each one of the words in the command line and then passes that into your program. And that shows up in your program as the argv variable. So this is, in fact, the way that command line arguments are handled by the shell. Okay, so where we left off last time was this idea that maybe what we could do if we want to crack these hashes is instead of when we run through this array of strings, hashing each one of the words as we go and then comparing it to our target, why don't we pre-hash all of the words? So we're going to do a lot of work up front, but it should pay off in a faster cracking of a whole bunch of passwords. If you only have to crack one password, it doesn't really do much good to do all this work up front. But if you have to do like 100 or 1,000 of them, it might be worth the time to do that. So let's see what we're going to do here. So we've got this array of strings, and what we need to do is build a new array of hashes. So we're going to build a parallel array, one that has the same number of entries, but it's going to contain the hashes rather than the words themselves. Now, one of the nice things about the hashes is they are all exactly the same length. You see, these words here are all different lengths, and so that's why I didn't want to create just a two-dimensional array. I could have created a two-dimensional array. I could have created like, one with, let's say, 100 entries over here, and each entry has 20 characters. But the problem with that is that the words are relatively short. So there's a lot of wasted space in this array. I could surely shrink the array down to just the kind of the minimum required, but there's still some wasted space. Whereas if I do it this way, there's no wasted space. Like every single word is packed up right against every other single word. There's no extra blank entries, but there is a little bit of overhead in maintaining this second array that points to all of those individual strings. So this idea of creating a two-dimensional array with a width and a height would work for the passwords, but it wastes a lot of space. However, for the hashes, this might be a way to go because all of those hashes are exactly the same length. Every single one of those hashes is exactly 32 characters long. So it would fill up the space exactly. So there's one possibility there, is that we could just build a 2D array of all the hashes. And the other possibility is just to do this second hash array the same way that we did the password array. Just create a large string with all of those hashes and then just build up pointers to them. So no, actually, let me not erase it. Let me just show you the alternative. The alternative would be to build a long array. It's got a hash and then a null character, and then another hash, and then a null character. And then a third way that we could build this, so this is option number 1, this is option number 2, and option number 3 would be, again, to have an array of pointers. But rather than each one of these pointing to a position within this larger array, each one of these individually could point to one of those hashes. So there's a hash here and a hash here. And a hash here. So this is option number 3. So all of them kind of accomplish the same goal, which is to have an array of hashes that we can index into, and every index in this array corresponds to an index in this other array. So the two-dimensional array would save a little bit of space in the case of hashes because we would fill it up exactly, and it would use exactly as much space as we need. The only downside there would be, well, I guess from kind of a educational point of view, it doesn't match the way that we set up this array here. So it could be useful to see an alternative way to set up the array, or it could be useful to see it just set up the same way, so they kind of like work in parallel with each other. Why don't we go ahead and do it this way here, the two-dimensional way, just for the sake of seeing it a slightly different way of setting it up. Okay, so we're not going to search for this target yet. We're going to build a parallel array of hashes here. So the first thing to do is to allocate memory for that. We know how tall it's going to be because we know how many entries there are, and we know how wide it's going to be because we know that the hashes are exactly 32 characters each. Let me think about this. Hold on a sec. So the question is, can I do it on the stack? You know, that's a good question. I could conceivably just do it on the stack. However, if the dictionary contains hundreds or thousands of words, then I couldn't do it on the stack. There's a limit to how big you can make a single array on the stack. I think the stack is like a megabyte or so. I've shown pictures where it just grows downward, but that's not really actually the case. It does grow downward, but there's a fixed size to that stack segment, and so it will grow downwards. And if it hits the limit of that stack segment, then the program will crash. So we could make it on the stack. We just can't make really big things on the stack. Hold on. I'm just pondering whether it will be as easy to do the two-dimensional array as I'm thinking it will be. And I don't want to go down a road where it is not as easy. Well, I guess let's just give it a shot and see what happens. And to be honest, I have not actually done this particular technique before, so I'm kind of going into this blind, as anyone would be when they're pondering these choices. So I think we'll just kind of go down this avenue and see if it takes us where we want to go. And if it doesn't work, we can always back out and try one of these other techniques. So we're going to allocate a two-dimensional array, which means we're going to call malloc, and now we have to give it how much memory to set aside. Again, we know how many rows it's going to be. That's num entries. And we know how wide each row is going to be. It's going to be 32 plus one more for the null that marks the end of each string. So it has to be 33 characters wide. And then we're going to multiply that. Well, we could stop here because we know that each one is a character, but just for the sake of completeness, let's put in size of character here. Okay, so we got the number of rows, we have the number of columns, and then we do size of character. Again, I just want to show you the idiomatic way to use malloc, which is you put the dimension first and then you multiply it by the size of each element. Here, the size of each element is just 1 byte because they're characters, but just so you see that same pattern over and over again, I'm putting it this way. Okay, and then what do we get back? Let's call this hashes. But what type of thing is hashes? Right? We're going to get back something that points to this thing. It looks to me like this is a pointer to a character, because this arrow here is pointing to just one single character. It's pointing to that very first character of the very first hash in this array. But here's where I was running into a little bit of difficulty when I was kind of like pausing and thinking about this. Is the very first hash in this array is hashes 0, and the second one is hashes 1, right? And the third one is hashes 2. But because the type of hashes is just a character pointer, this is not actually pointing to the rows of the array. It is pointing to the characters in the array, and I want it to point to the rows in the array. Oh, you can't see what I'm looking at. I'm very sorry about that. And the thing is, this is not a character pointer either, because hashes is not pointing to a pointer. It's pointing to a character. That's what it's actually pointing to. So what we need to do is convince the compiler that although we got back a character pointer, it's actually a two-dimensional array. So I think we're going to use a cast in order to get that done. So malloc is going to return a single character pointer to us, but we're going to say that it's actually a character two-dimensional array. I wonder if we can do that. I don't know. Let's give that a shot. I'm going to save it and we're going to compile this. Oh, no, it's not allowing that. Oh, array has incomplete element type because it needs to know how wide each thing is. So we'll put 33 there. Sorry, the 33 goes over here. Cast to incomplete type. No. Let's put in a character pointer here. I'm just like fiddling around here. Array initializer must be an initializer list. Oh boy. Well, let's look this up. Let's Google for that. Let's go for C cast malloc to 2D array. How do we allocate a 2D array using one malloc statement? No, that's not what I want. Oh, here it just says make it an integer pointer. Oh no, this is actually an array of arrays. It's not what we want. Oh boy, number of rows, number of columns, integer pointer. See, this is why I looked at that and went, oh, I don't know if this is going to work, just because we have to do some tricky stuff with casting to make this work. So the question was, can we just manually add 33 every time? That's one possibility, is we just treat it as one array of strings and we just jump our way through it. Again, we could do that, but we want to lead up to a way to ultimately be able to reorganize the array into a better ordering. So it would be nice if we could index into the array directly and just treat it like it was just an array. Nope, that's not what we want. See, ultimately the problem here is that malloc doesn't know what this memory is going to be used for. You just tell it how many bytes to set aside, and it just does that. So it thinks it's just allocating one chunk of memory that's just an array of whatever it is you're allocating, an array of bytes, an array of characters, an array of integers. It doesn't know what that memory is going to be used for or how it's going to be used. But we know that we are allocating space for a two-dimensional array. So we're trying to get it to set up so that the chunk of memory returned by malloc can be treated by the program as though it was a two-dimensional array, as though we were doing character hashes with the number of entries as the first index, or the first dimension, and the width as the second dimension. We want to do this so that we can just say the first hash is number 0, the second one is number 1, and so forth. But malloc just returns a single pointer to this chunk of memory, and we're now trying to convince it that this is something different. So I can't just say that this is a character pointer because it's not. It's not a pointer to a thing that points to characters. It's just a character pointer. It's just that we're treating it as a two-dimensional array. I wonder if we can do character pointer h and then do something like character hashes equals h. I don't know if that will work, but let's try it. Nope. Array initializer must be an initializer list. So when you set up an array like this, could it be a character pointer hashes? No, it's not an array of character pointers. It's just an array of characters that happens to be broken up into a chunk that's 33 characters wide. I guess this is why I'm not a big fan of two-dimensional arrays in C when it relates to using malloc. And we can see over here in this Stack Overflow discussion that there's not like just an easy, like just do it this way. Not just an easy answer. Oh, let's see. So this is, oh, So here's, I'm looking at this. Here's what we want to do, right? And so here's a integer pointer with each one. Oh, okay. So maybe Ivan was correct. I'm looking here at the message, the text, the comments. So maybe he was correct. Can we do it like that? Must be an initializer list, but there's a cast here, right? No, I don't think this is really answering our question, because in this case, the compiler knows what the dimensions of the array are, and then you're just casting it to a pointer that points to that thing. But in our program, the compiler, or at least the malloc, doesn't know what the dimensions of our array are, and so can't do that. Ivan says it works. How did you get it to work? Oh, maybe what I need to do, like it does, is put this in parentheses so that we kind of, we say that H is the character pointer, not the array is the pointer. Let's try that. Nope. Incompatible pointer types. Okay, well let's then let's say that this is a character pointer. Nope. Let's say that this is a character. Oh my goodness. Character array. Nope. What, all the shenanigans we have to go through to get this to work. Oh, let's take away the cast entirely. Wait a minute, that might have worked. All right, the reason why that might have worked is because when malloc returns, it just returns this generic pointer type, and then we can cast it to be whatever we want. And so maybe this worked. Okay, so this says that H is basically an array. Each element of the array is 33 characters wide. I think this might have worked. This will be amazing if it does. Okay, so allocate a two-dimensional array, and then we are going to pre-hash each entry in the, what is it called, the entries array. Oh, let's call this hashes instead of H. All right, I'm excited about this. Okay, so we're now going to loop through the entries array. And then we're going to call MD5 on each one of those entries and store it away in the hashes array. So we'll go character pointer hash equals MD5 of entries I, comma, string length of entries I. So after we call MD5, we now have a pointer to that hash, and then we can use string copy to get it into the array. Why don't we just use an assignment? Because we are, what we're given back is one single array of 33 characters, and we want to store that into that two-dimensional array that holds hundreds of characters. And so the only way to do that is to copy. So let me draw this picture here. So we're given back one single string, and we called that hash. And we want to get it into here. So we have to copy every single character out of this array and into this one. We have to do that with string copy. So we're copying from one array to another array, and so we have to use string copy to do that. Ivan, so the question was, can I just do this? And the answer is no, because now hashes is a one-dimensional array, but we want it to be a two-dimensional array. So putting in this width dimension there makes it now a two-dimensional array. I hope makes it a two-dimensional array. Okay, so we pre-hash each entry, storing it to the hashes array. So we hash each entry, we copy it into the hashes array, and that should be it. So we now have this array filled up with all these hashes. So let's go ahead and print that out. See what's there. So I'm going to print out my counter, and I'm going to print out each entry of the hash. Okay, and then let's just exit the program at that point. Say we're done, right? I don't want to do any of the searching stuff yet. Oh, I'm kind of excited. This might be. Oh, that's right. I need to. I'm so excited. I forgot to compile with md5.c and link to the crypto library. Oh, what's going on here? Oh, because at the top I need to include md5.h. Oh, it compiled. So let's run this and let's give it the file that we're going to be hashing, which I think is this one right here. Whoa, look at that. We got hashes in there. Okay, so the first entry here is pizza. Let's go ahead and go echo -n pizza. Pipe that into MD5 sum. And so this is what MD5 says is the hash for pizza, and we got something, oh, we got something different. Uh-oh. The next one is sushi. And we got, wait a minute. That one's the same. Okay, for sushi, that one's the same. But for pizza, oh wait, no, it is right. It is right, the same one. I was just looking at the wrong one. I just need to scroll this up so I can see both at the same time. Okay, so here's the one for pizza, and that's the 0th entry. And here's the one for sushi, and that's the entry there. So Ivan, you said that you left off this, and it still worked? Yeah, see that doesn't work because now it thinks now that hashes is just a one-dimensional array of characters. But by putting on this second dimension, it now knows that hashes is a pointer to a two-dimensional array. And you know what? I learned something today. I learned now how to take a malloc and convert it into a two-dimensional array. I did not know that before. So there you go. The teacher learned something today. Well, you know, it does seem complicated because we spent a lot of time looking it up. But now that we see the solution, this makes sense to me. You know, if I leave off this second dimension here, what I'm saying is that hashes is a one-dimensional array. It's just hashes is a pointer to an array of characters. But by putting on this second dimension here, I now have told the compiler that hashes is a two-dimensional array. So the first dimension is here, and the second dimension is over here. And you have to put the number in there so that it knows how wide each row is. You can't just leave that number off because then it has no idea how wide the array is. Okay, so now watch this. I should now be able to print out both the password and the hashes with one single loop because I've got two arrays that are running parallel to each other. So let's try that. So let's print out the hash followed by the corresponding entry that goes along with it. Look at that. So we got the hash and the corresponding entry and the hash corresponding entry. So you can see that these two arrays are running in parallel with each other. The nth element of the hashes array corresponds to the nth element of the entries array. So now let's take out that exit, and we're going to have it do the search, but now we're going to paste in a hash that we're looking for rather than the individual entry that we're looking for. So here's our target. We're going to loop from I to, what is E again? E. E is, oh, E is the length of the entries array, and we also have num entries, which is the same thing. So I'm going to switch this around. This should be num entries. I mean, the values are the same, but this just is a more wordy and descriptive variable. So num entries here. So if the target is equal to hashes I, then found %s %s. Okay, so and then we'll print out the hashes I and the entries I. Okay, so we've built up our two parallel arrays, and now let's do a search. Let's look for maybe this one here. So we'll paste that in, and it says it found it. So it found this hash, and it corresponds to the word salmon. Very cool. So now let's try running this again, but let's pass in the rocku 100 file. Okay, so there's 100 entries in there, and let's look for this one. Yep, there it is. Okay, so let's recap this program. The first part of it's the same. We still load in the file of plain text entries, same way as before. So this is all the same. This is all the same. Here's the new stuff. Build a parallel array of hashes. We know how wide each one of the hashes. We know they're 32 characters wide, plus the null that terminates the string. So they're a total of 33 characters wide. And we know how many entries there are. That's sitting in the num entries variable. So if we multiply those two numbers together, we've got the total number of bytes we need to set aside. So we ask malloc, multiply those things together, set aside that number of bytes, and then we cast it to a two-dimensional array. The first dimension is here. We just get back a pointer to this data structure, and each row of the array is 33 bytes wide. We have to tell it how wide the bytes are so that it can do the calculation correctly, so that in order to calculate the memory address of one of the particular hashes, it can do that correctly by multiplying the row number by 33. And that tells it how many bytes into the chunk of memory to find that particular hash. Then we just loop through the entries array, pass each entry into MD5, get back a hash, and then copy it into the hashes array. And we can just index into that array just like it was any other array, although it's an array of strings rather than like an array of numbers and an array of doubles. And then finally, we can search through that array. Just start at the top, go down, search for the hash that we're looking for, and then sitting at the corresponding entry in the entries array is the plain text password. So this should save a lot of time if we have to crack a whole bunch of passwords. If we only have to crack one password, this doesn't save much time. Actually, it probably doesn't save any at all. But if we have to do a whole bunch, this will save time because now we don't have to open the dictionary file, read in each word, hash it as we go, and then close the file. Nor do we have to read in each entry of the dictionary, hash each one, and then throw that hash away. And then the next time we want to crack another hash, do that process all over again. So by pre-hashing all of the passwords, we can spend some more time up front in order to save time later. But as we've seen, this could be slow because we don't know where in the array that hash that we're looking for is. Could be near the top, could be near the bottom. And if our dictionary is really large, let's say it holds 1 million entries, that's a lot of things to search through. We could potentially find it near the beginning, or we could find it all the way down near the end, or somewhere in the middle. If we had 1 million entries, what would be, let's say, the average number of entries we would have to look at before we found the hash that we were looking for? So if we had an array with 1 million entries in it, and we're looking for one specific entry in that array, what's the average number that we will have to look through in order to find what we're looking for? About 500,000, about half of them. Sometimes you get lucky and it's towards the beginning. Sometimes you get unlucky and it's towards the end. So the average is about half. Could we do better than that? Absolutely, we could do better than that. If we could organize the data so that we could search for things quickly, then we could speed this up tremendously. And that's what we're going to be doing when we come back from our Easter break. In order to search it quickly, we've got to put each one of those hashes where we can find them quickly. And one way to do that would be to sort the array, essentially numerically or alphabetically, so that the zeros are up near the top and the later ones are down near the bottom. Then you can do something called a binary search. When everything is sorted, you can be more intelligent about how you look for something. Start in the middle, and then if that's the thing you're looking for, you're done. If it's not the thing you're looking for, and let's say the thing in the middle comes after the thing you're looking for, well, now you know the thing you're looking for must be in the first half of the array, and you can ignore entirely the second half of the array. So already you've reduced the size from 1 million to 500,000, and then you repeat the process over again. You go halfway, and then you see which half of that array is the thing I'm looking for in, and if it's not, and you can throw away the half that it's not in. So you can quickly winnow down the element you're looking for. This type of search is much, much faster than a linear search, which just goes from beginning to end, at the expense of having to sort all of the entries after you read them in. So again, more work up front for a bigger payoff later. Again, if you're only cracking 1 or 2 hashes, this probably doesn't make any difference at all. If you're cracking a whole bunch of them, then this does make a huge difference. So that's what we're going to do when we come back from the break. We're going to learn how to sort and learn how to search. Any questions about the program that we've written so far? Oh, so Akash, that's a really good point there, that if you're going to sort the hashes, you also need to do the corresponding sort to the entries. Now you can't sort them separately. You can't sort the hashes, let's say numerically, and then sort the entries alphabetically because they won't necessarily line up. In fact, they're very unlikely to line up correctly. You want them to be in corresponding entries, so that if the hashes are in numeric order, the entries are in the same order that the hashes are in, so that the entries correspond. Which means when you're sorting the hashes array, you also need to be sorting the entries array in the same manner. So that if I, let's say, move element number 5 in the hashes array to position number 0, I also need to move element number 5 in the entries array to position number 0, so that they line up with each other. So that kind of poses a problem. I mean, you could write a sorting function that would do exactly that, but the C standard library has a built-in sorting function, but it only sorts one array. It can't sort two arrays simultaneously. I mean, there might be a way to intercept its sorting algorithm, but it just doesn't do that by naturally. So we would either have to write our own, or we'd have to do something a little bit better. I think before I move on, I want to draw your attention to this one right here, number 3. So what we did up till now was build this data structure. But what about this one here? What are some of the advantages and disadvantages of this one? Well, the disadvantage of this one is that there's this overhead of having an additional array, one additional array that points to these individual things. And the other disadvantage here is now there's a whole bunch of mallocs. Every single one of these hashes is stored in its own allocated memory chunk. But the advantage of this one could be it just maybe is easier to construct. Remember, we had to go through all sorts of research just to find out how to build this data structure using malloc. This one here is very easy to do because malloc works with one-dimensional arrays very easily. So if we look here, we see that we pre-hash each entry, storing it in the hashes array. When we call MD5, what does it return to us? Remember, it returns to us a single string containing the 33 characters of the hash. That's 32 for the characters plus 1 for the null. In other words, it returns to us one of these things. So if we want to build this data structure, MD5, the function MD5 has already done like half the work for us. It's already allocated one of these things. Notice in our program here, it allocated one of those things and then we just threw it away. We didn't do anything with it. In fact, we ended up copying all of the characters out of that thing and putting it into the hashes array. And it just occurred to me that every time we did that, since we threw away the return value from MD5, we now have some memory leaks. Let's go ahead and run the program again and see if we leaked any memory. So let's recompile it and put in the -G. And then let's also, oh, well, let's just run it. So we'll go valgrind a.out. Oh, that can't be right. No mallocs, no anything. Oh, because I didn't do the usage correctly. So I have to put in, let's put in some text.txt. Here we go. And then we'll search for this one. And it found it, and then we get this here. So in use, 587 bytes and 10 blocks, and we lost 518 of them in 9 blocks. Now if we run the program again with --leak check equals full, it says here that we've been doing mallocs on line 46 and on line 62 and on line 67. So here's a malloc that we're losing, and on line 67, here's mallocs that we're doing. They're actually embedded inside the MD5, and on line 46. So what we're not doing in our program is freeing up any of this memory. So where would we put some free statements in order to free up this memory that we're allocating? Well, one place to put it would be after we call MD5 and copy its entry out, we can just free that up because we don't need it anymore. Well, that seems to be a bit better. We brought it down from 587 to 287. Now there's only 2 blocks of, that need to be freed up. So when our program is completely done, we need to free up this one, and this one. So we can free up entries. That's this one. We can free up contents, which is this one. And then we can free up hashes, which is this one here. So this is what I've got. And that's what we want there. No memory in use. Everything's been freed up. Perfect. So we had to do a free inside of the copy, and then 3 more frees in order to free up all the chunks of memory that we had allocated. So essentially, every time you do a malloc, remember, put in a corresponding free. It's probably a good idea to put those things in as soon as you can so you don't forget about them. So do you want to see us build this data structure here, or should we move on to something else? Actually, we only got about 20 minutes left, so I'm thinking we can move on to something else, and then we can maybe revisit this thing the week when we come back. Oh, Akash says, let's build that one too. Let's see what we have time for, okay? I want to show something else. So this is kind of switching gears a bit. Don't think about passwords for a moment. Let's think about like Disneyland. Whoops, I didn't spell that correctly. So here's Disneyland in Los Angeles, California. And we can actually see in the address for this pin that I just dropped right here, we can see its GPS location. So it's 33 degrees north, negative 117 degrees west. I'm going to write that down. 33.812 degrees by negative 117.921. So I just wrote down quick little notes about the location of Disneyland. What are some other well-known locations to you? Why don't you put something in chat? What are some other well-known locations to you? Well, I'll answer this question. Are the hashes lost after the program is done? Yeah, after the program is done, all the memory is erased, and we would have to start all over again and pre-hash everything when the program starts up again. So there could be another optimization, which is pre-hash everything and then store it away in the file. So the next time you run a program, all you got to do is just read those two files in, and then everything goes really quickly. So let's put in a few more here. Let's put in, while you're thinking about that, what are some other landmark locations around the world? Let's put in the, I don't know, Eiffel Tower. Oh, I want to do that on the maps so I can get its location. So up here is the GPS coordinates for the Eiffel Tower. .853 and 2.291. What else could we put in there? I want a few more. Few more well-known landmarks for you. Let's go with the London Eye. (51.503 by negative 0.121). The Gol Gumbaz. At 16.830 and 75.734. And the S, is that St. Marco? S. Marco Place in Venice. This one here. I think that's probably it. And here's its GPS coordinates. Okay, so I got 5 places. It's good enough for now. So each one of these 5 places has a name and a latitude and a longitude. So we got 3 pieces of information to store about each one of these landmarks. Now we could store them in 3 separate arrays. We could store them in an array of names, an array of latitudes, and an array of longitudes. Or, and this is the solution I want to propose to you, we could store each one of these in a structure that each contains a name, a latitude, and a longitude. Here's how you would do that in C. Let's call this landmark, struct landmark, and then we're opening the curly braces, and we'll put in 3 variable declarations. Let's set aside, let's say, 30 characters for the name. A float for the latitude. And a float for the longitude. I can't call it long. I have to call it LON. And then close the curly braces, and then a semicolon. And this right here is one of the few places in C where you'll find a semicolon sitting after a brace. So this little snippet of code here is not actually anything executable. It's just a declaration. It says that we've got something called a struct landmark, and it contains these 3 fields with these 3 types. So it will now store all 3 of those things together in memory and give it one single name. And then if we want to make a variable for one of those landmarks, we say struct landmark and then the variable name. Let's call it like LOC for location. So the name of that location is loc.name. The latitude for that location is loc.lat. And the longitude is loc.lon. So use the dot notation to access each one of the fields of that structure. So let's build a program that can store the name, latitude, and longitude for a couple of landmarks. Declare this structure outside of your functions. It's a global declaration, so it goes outside your functions. Struct landmark, character name 30, float latitude, and float longitude, and then a semicolon. So every time we allocate space, whether it's on the stack or the heap, every time we allocate space from one of these landmarks, it sets aside 30 characters for the name, plus I think 32, 4 bytes for the latitude and 4 bytes for the longitude. So a total of 30 plus 4 plus 4, 38 bytes. And then just lines them up side by side in memory. When you set aside space for one of these structures, it allocates space for all of the fields of the structure and lays them out side by side in memory. Is it possible to declare structs inside functions? It probably is. You don't usually do that because the structure might be needed by a couple of different functions. It might be needed by main, and it might be needed by some other function as well. So you want to put those structure declarations usually outside. If you do have a structure declaration that is only needed within one function, then you can probably put it in there, but it's not typical to do that. So I'm going to ask the user to enter the name of a landmark. And then here's my ordinary scanf, reads in a string, and it just puts the name of that landmark into loc.name. Then I'll do a scanf for a float and put that into location.latitude. And here I put in the ampersand, just like I've always done when I'm reading in things like numbers. Just put it in front. And another float for the longitude. And then finally we could print out those three fields. Let's just print them all out like all at once. So not separate lines, but one single line. So let's put in %s and then %f, comma, %f. And we'll do location.name, location.latitude, and location.longitude. Okay, name of landmark, Disneyland. Latitude, 33.812. Longitude, negative 117.921. And then here we go. Could the structure be more than 38 due to padding? The answer there is yes. It's not usually a detail you have to worry about, but I think on most systems, if the structure ends up not being a multiple of the word size, which is probably a 32-bit quantity on an Intel processor, then it will round up to the next multiple of 4 bytes. So the 38 here will probably get rounded up to 40 bytes with 2 bytes left over with what's called padding. So allocated as part of the structure, but not really accessible. Line 15, is the ampersand missing? Here it is not missing because name is an array, and when you pass arrays into scanf, it already goes in as a pointer. So you do not need the ampersand for strings. You do need it for the primitive types like floats and integers and doubles. Okay, so you see here how to declare a structure and then access each one of the elements of the structure. What if we have more than one? Well, we could create a second variable, like location 1, location 2, location 3, for each one of the locations, or we could create an array. Create an array of structures. So to create an array, you just put the braces or the brackets after the name of the variable and then the dimension that you want. Here I've got 5 entries. And let's just put this in a loop. And then all I have to do is put in a bracket with I after each one of these references to location. So this is the ith location and the name field within it. And then I can run a loop again to print them all out. Okay, so name of landmark 0, Disneyland. Latitude, 33.812. Longitude, negative 117.921. And then we move on to the next one. Now, one of the shortcomings of scanf, if you remember, is that it only reads in a single word. So it's going to stop at the first space, which means if I want to put in a word with more than one space in it, I really shouldn't be using scanf for that. So what I'm going to do is, in order to put in Eiffel Towers, I'm just going to run the letters together. Again, we're just doing this for testing purposes, just to see what happens. .853 and 2.291. And then the Gol Gumbaz, 16.830 and 75.734. And finally, St. Mark Place, 40.434 and 12.335. Okay, after I enter this last one, we're going to see this just going to print out all of those landmarks, each one on a line by itself. What if we entered things like Eiffel Tower with quote marks around it? That's not going to help us. With scanf, quotes are considered just one of the characters you're entering. So the string just goes in with quotes. It still stops at a space. The scanf is really not that smart. It just simply starts at the first character and goes until it hits the first white space, which is either a new line or a space or a tab, and then it just stops at that point. Okay, so what did we learn here? We learned about how to declare a structure, how to allocate the elements of the structure, just using the dot notation. You've seen that in Java before, right? So it's very similar to that. And then finally, how to create an array of these structures and then allocate access the elements within that. Okay, so how do we, this will be the last thing, how do we pass structures around into other functions? Like here, I'm printing out the elements of the structure. I'd like to be able to take maybe this portion of it right here and create a function out of that. Still going to have a loop that goes over the whole array, but I want to have a function that prints out just the elements of the structure. So let's make a function called, let's call it like print landmark. We're going to pass in a landmark that we want to print the information out about. So this is a struct landmark, and let's just call it LM. And this function is not going to return anything. It's just going to print stuff out to the screen. And inside here is our printf. But here, print landmark doesn't know anything about the array. It's just being passed one single structure. So there's no need here for this array notation. As far as print landmark is concerned, there's only one structure to one landmark to print. So we can call this print landmark from within a loop, or we can call it individually on an individual location. And it doesn't know or doesn't care where the data comes from. All it knows is that it's handed information about one single landmark. So let's save it, compile it, run it. Oh, I got to enter everything all over again. That's crazy. You know what I can do is I can take advantage of the fact that this is running on a Linux machine. I could put this information into a file and then just have it read in the data very quickly. Let's go ahead and do that. You might be able to, so I'm going to not alter the program itself. I'm going to take advantage of the shell's redirection in order to get the input from a file rather than the keyboard. But you can probably see where this is going in the future. Instead of getting the information from the keyboard, I'm going to rewrite it to get the information from a file directly. But we're not going to have time, I think, for that today. So now I can just say a.out and then redirect from landmarks.txt. We're going to see a whole bunch of text go by as it prompts for all the information, but we won't see the data being entered itself because it's being redirected from the keyboard, redirection away from the keyboard and towards this file. So it prints out all of these prompts, but then finally it prints out the information that's in the array itself. And you can see here that we're just calling print landmark 5 times, and every single one of those print landmarks prints out just information about one location. So this is a good reason why I want to declare the structure outside of the functions so that both print landmark and main know about this structure. If I was to put this declaration only within main, then print landmark wouldn't know anything about it. And if I put them inside of both, the compiler might complain that these are just 2 structures that happen to have the same name, but are different structures and therefore can't guarantee that the entries, the fields within them are going to line up the same way for both of them. So it's better to have the declaration outside so that both functions get access to it. So let's see, where can we go from here? I could probably spend a few more minutes on this. How about doing a search? Why don't we search through this array of locations and see if we can find one of them? Oh, let's see, your question here is, do we get a reference to the struct or we get the values within the function? So when we are calling print landmark, we're not passing in a pointer to the struct, we're passing in the struct itself. So when you pass in the struct, it makes a copy of the struct. All the information that's in the struct in the array gets copied into a new structure that gets passed into print landmark. So what you get inside of print landmark is a copy of the data that's in the struct, not a reference to the original data itself. We could pass in a pointer and then we would get a reference to it. But the way we're written it here is you get a copy of it. So yeah, if the structure is big, like it contains some huge strings and a large amount of data, that's a lot of extra work that the compiler needs to do in order to pass you a copy of it. But that's what's going to happen. You're going to get a copy. Actually, let's go ahead and do this. So we've got a little bit of extra time. let's go ahead and do this. We are going to modify this program so that it gets the information about the landmarks from a file, so I don't have to do the redirection stuff. And then also we're going to have it do the search. So let's have it read from the file rather than prompting for keyboard input. So we're going to come up to main, and main is going to contain the name of the file that we want to read in on the command line. So we're going to modify how main is declared. We're still going to declare this landmark structure, but let's maybe have space for 10 of them. We don't know how many it's going to be, but maybe space for 10. And then we're going to have it read in landmarks until it hits the word done on the very last line. So if we got a done sitting here, then it will stop reading in. So let's open the file for reading. File pointer in equals fopen argv1 for reading. Let's check to make sure that it actually opened that file. And then exit if we can't open it. And now, here's how I would suggest reading in data from a file. We could use 3 separate scanfs, but we could actually condense it down to 1 scanf. So we've got here 3 separate ones, but we're no longer going to prompt the user. We're no longer going to see any prompts on the screen because we know all the data is coming from the file. So we can get rid of this printf, we can get rid of this one, we can get rid of this one, and that leaves us with just 3 scanfs, which we could combine into 1. We can do %s, %f, %f. And then just put in the 3 references to the 3 fields of the structure. But this doesn't take into account that we might have an entry that contains just the word done. The problem here is that we're expecting to see a string followed by 2 floats. But for landmarks, there could be just a single string and then we're done. We're all finished. So I think, and this is my personal preference here, my preference would be read in the line using fgetS. So it can pull in the whole line and then break it apart separately using one of scanf's cousins. So here's, I think, a good way to read in a data file when the format of the various lines in the file are going to change. They're not all exactly the same. Hello, John. Good to see you here. So we're going to use while fgetS, our good old friend fgetS. And then we're going to read it all into a single line and then break it apart separately. So we've seen this recipe before, using fgetS inside of a while to read in each line. Now we can check to make sure, we can check to see if the word done appears on the line, and if it does, then we'll just exit out of this loop and we're done reading in the file. So if string compare line done is equal to 0, then we're done with this loop, right? We can just break out of it. Actually, I'm sorry, we don't even have to do this. We don't have to do this. We can just check to see when the file ends, so we don't actually have to put this done in here at all. I am totally going on a complete tangent here. I still like this idea of reading it in using fgetS and then breaking it apart. And then now we see there's a comment here. We could actually remove done from the text file. You're absolutely right. We could have done that. Okay, so now we're going to use scanf, its cousin scanf, to scan through a string and break it apart. So we read in the line into one giant string, and then we break it apart using scanf. I still like this technique for one really good reason, and that is when you read lines in with fgets, it places a limit on how long that line can be. So if a nefarious actor produces a landmarks file that has a line that is too long, it won't break the program. With scanf, there's no protection about how long the line can be. So if somebody puts in a string that is more than 100 characters, or more than whatever this name can hold, then the program will potentially break or crash. So the nice thing about fgets is you can now accommodate longer lines of input and then break it up individually. And you're right, we still have a problem where if this string is longer than whatever the name can hold, then we got a problem. But like I said, I still like this technique. All right, let's see if that works. Oh, let's close the file when we're all done with it, and then print them out. Uh-oh. Use of undeclared identifier I. Oh, I see. I see what we've got going on here. We need a counter. Oh, more errors. Use of identifier line. I forgot to put the type in front of this. And now we need standard library for the exit. Okay, all right, so a lot of your debugging time is spent just getting the compiler to be happy. There we go. Perfect, that's what we wanted. So we've got no prompts at all. It just simply prints out everything that's in that file. So now we can make the file bigger. We can add more. If we wanted to, we could add up to 10 landmarks to this. We've only got 5. We can do up to 10. And in fact, the value I here contains the number of entries that are in the file. It starts out at 0, and as we go through the file, we increment that number. So by the time we get done with this loop, this variable I contains the number of entries. So I think it might be a good idea to change this name. Let's call it num entries, right? So that it reflects more what its purpose is. Okay, and then here I'll put num entries. And hopefully this will work. There we go. Perfect. All right, so this is the last thing we're going to do. We are now going to do a search on this. So we're going to maybe prompt the user to print to enter a landmark they want to search for. Just do a quick scanf on that. Actually, let's use an fgets on that. Let's remove the new line character if one is there. And then we'll do our search. So for integer I equals 0, I is less than number of entries, I++. If string compare, target, and the ith entry of the landmarks, name is equal to 0. All right, see that? So we're looking at the ith entry of the locations. We're accessing the name field of it and seeing if it's equal to our target. So we'll print out found, and then we'll go ahead and call print landmark. And then we'll break out of the loop. All right, I think we're getting somewhere here. Oh, now we need string.h. All right, zip up to the top, add that one. No complaints now. Okay, what landmark to search for? Let's search for the London Eye. And there we go, found it. So when we do this search, we're looking only at the names. So there's no general purpose see if this structure is equal to this other structure method, but we can use the string compare function to look at the individual names. So this one here won't search by location, it only searches by the name of the landmark. How could we get it so that we didn't have to type in the exact name? So that we could type in just a portion of the name and it would tell us if it's there. So instead of using string compare, which does an exact string match, what do we use instead to let us type in just a portion of a name and let us know what it found? Do you remember what string function it is that lets us do that? No, it's not substring, although you're close. What could it be? So I'm not worried about case insensitive at this point. Just search for a string within another string. Let's look through our list here. That's not it. That's not it. Memcopy? No. No. Memset. String cat? No. We already know string character here for searching for a character within a string. So that's not quite what we want. We want to search for a string within a string. String compare for doing an exact string comparison. String n compare for comparing at most the first n bytes of the string. But that's not really what we want to do either. I want to be able to type in something like just I and have it find the London Eye. Another string comparison, but this is again a full string comparison, so that's not it. String copy, no, that's not it. String error, string length. Here's what we want. String. Find the first occurrence of the string needle, which appears within the string haystack. So string is what we want. And if we wanted to do a case insensitive string match, then we would have to either write our own or we would have to do some kind of transformation on the strings in order to get it so that the case matches. You do that by either converting all the letters to uppercase or all the letters to lowercase in both the target and the thing you're searching for. And then once you do that, you just simply do a string compare. So let's use string. We still pass in our target. and the thing we're searching for. Oops. So what comes first? For string string, the haystack comes first, and then the thing we're searching for. So that means that the thing we're searching for is target. We need to switch these around. So here's the string we're looking within, and then here's the target we're looking for within this string. And so if this thing returns something that is not equal to null, then we know that we found it. So if we just search for I, then it found London Eye. Very good. And if we search for TOW, it finds Eiffel Tower. And if we search for just G, then it finds the Gol Gumbaz, because it actually finds this first G within the name. If I type in a lowercase g, it doesn't find it because there's no lowercase g's anywhere in my strings. So I'm pausing for a moment to think, like, is there anything else we could do to this? So, I mean, like, what have we done so far? We've actually done quite a bit. Like, we learned how to declare a structure. We learned how to pass a structure into a function. We learned how to create an array of those structures and then read lines in from a file using, I like this technique of using fgetS to read in the whole line and then break it apart using scanf. Another reason for liking this technique is, let's say you want the file to just be a whole bunch of numbers. Right? You just got a file full of numbers. And then for some reason, one of the entries in the file is actually a string. Right? There's a stray character in there that's not part of a number. If you use just scanf to read through the file, and it encounters that string in the middle of all these numbers, it's going to freak out, right? It's going to see that string and possibly put like a 0 into your data, or it will ignore it, or, you know, it depends on where that string occurs within the file. Does it occur like, do the characters occur within a number? Do they occur before a number, after a number? So the behavior of scanf is going to change depending upon where those stray characters appear on that line that's supposed to contain a number. However, I could use fgetS to just read in the line no matter what it is, and then use scanf later on, like within the loop down here, in order to actually read in the number itself. And then my program's not going to break so much. It will find that line that contains the string, and then you can actually call scanf and look at the return code from it and find out whether it was successful at reading in that number or not. This technique sort of pays off more when your lines can contain more than one thing. Let's say each line contains 3 data points, you know, a number, and a number. Again, what if there's a string in the middle of that thing? Your scanf is going to totally break when it encounters that. But if you read it in using fgetS, pull that whole line in, and then break it apart using scanf, now you can do some error detection and error correction. You could actually read in that whole line and then quickly zip through that line and make sure it contains nothing but digits, and then use scanf to break it up. Or you could call scanf and then look at the return value and see whether it was successful or not at reading in those individual values. So this is why I like this technique of reading it in, because it allows you to accommodate errors or variations in the input data much easier than if you just use scanf, which is really brittle, right? Scanf works fine as long as the input contains exactly what you're looking for, and it just completely falls apart if there's any kind of misalignment in the data that it's inputting. So after we read in that file, we then have a function that prints out one individual structure, so it has no idea that this structure came from an array. And then finally we can do a search. We can prompt the user for a landmark to search for, and then just simply do a quick linear search through the array of structures, looking only at the name fields, and then print it out if we found it. And again, using our same print landmark that we had before, passing in an entry out of the array, but print landmark doesn't know that it came from an array. It thinks that it's just one single structure. And then that's it. It's pretty good. So where could we go from here? Here's some ideas that we could do. One would be, and this is what we're going to do probably next time, is could we sort these structures so that they go in alphabetical order? Or could we sort them numerically so they go from, let's say, south to north, or north to south, or east to west, or west to east? Instead of just printing out a landmark when we find it, essentially what we know is the element number. We know this I number when we find it. Maybe we can modify this so it doesn't pass back the index number, it passes back a pointer to the structure that we found. That could be interesting, because then we could do something with that. So that would involve passing pointers to structures around. Again, something we can get into next time. If we're able to sort the structures, then we can be more intelligent about how we search through it. We don't have to do a linear search from top to bottom. And this also would solve that problem that someone brought up about half an hour ago, which is if we have two parallel arrays, or in this case, three parallel arrays with names, latitude, and longitude, how do we sort those three parallel arrays so that the ordering of one also matches the ordering of the other two? Now that we have one array where each element is a structure, we can now sort the one array, and then all of the associated fields go along with each structure. So when we sort just by name, the latitude and longitude go along with it, and it maintains the ordering that we want. And ultimately, what we're headed towards is, instead of maintaining two separate arrays for passwords and hashes, do you see where we're going with this? We could store the password and its associated hash in a structure, and then sort those structures and search it really quickly. And then we don't have to maintain two separate arrays. We just got one array that contains both pieces of information. That's where we're going. And it's going to take us a little while to get there, because we have to learn about things like how to sort. And you've probably written a sorting function before. You might have written something like bubble sort, or merge sort, or insertion sort, or selection sort. You might have, in a previous course or during your studies, have learned about some basic sorting functions. But there's one that's built into the standard C library. So we're going to study sorting algorithms, and then a little bit, and then learn how to use that built-in one. And then we also learned about binary search. I'll show you how binary search works from kind of a conceptual level, and then we'll learn how to use the built-in binary search function to search through this array of structures and find the one we're looking for. So there's a little bit to learn between now and when we can actually implement this last password cracking program. So I'm not going to introduce it today, although those of you who are in my class, you can go ahead and take a look at it. But I will introduce that next time. So we're talking about 12 days from now. We'll see how that program is going to be structured, what it's supposed to do, and then we will tackle all the individual pieces that we need to be able to build that program. So I'm going to let you go off to Easter break with no new assignments. So if you want to spend, if you're going to be, not traveling, if you're going to be just staying around at home, or even if you are traveling, you could use the next week or so to catch up on some of your assignments. Again, in my course, I have this ungrading policy where I'm not penalizing you for late assignments, and all I'm doing is marking your assignments as being either complete or incomplete. So please take this opportunity to catch up if you've been falling behind on some of the assignments, so that by the end of the semester, you're not trying to do everything all at once. There's a lot of work to do if you wait too long. So again, take this opportunity and to try to catch up. Now, some of our lab assistants, I think maybe, I'll check with them, may be available during the break, so that if you need some help, you can contact them. Because I think, well, I'll talk to them and find out if they're willing to work a few hours. And also find out whether that's allowed, whether it's allowed for our students to work over spring break. So I think that's it for now. I've done a lot of talking, we've learned a lot of stuff, and then we're going to put some of those concepts together when we come back from the break, and then be able to finally tackle this last password cracking program. So the last thing is, please explain this redirection. All right, let's see if I can quickly do that. So conceptually, on a command line environment, you've got your program, whatever it is. And there is a source of input called standard input, which comes into your program. And you've seen this stdin before. Whenever we use fgetS, we pass in as that third parameter this thing called standard input. And there is also standard output for output from your program. And there's one more out there called standard error. So error messages typically go to standard error, and regular output goes to standard output. By default, standard input is connected to your keyboard. So any characters you type on your keyboard go into this thing called standard input, and then they go into your program. So your program actually has no idea that input is coming from the keyboard. All it sees is that input is coming from this nebulous thing called standard input. And by default, your standard output and your standard error go to your screen. Oops, it's up there in the corner, but you can't see it. I'm going to turn off this. And again, your program has no idea that it's actually sending characters to your screen. In fact, it's not, of course, directly connected to your screen at all. It goes through the internet to get to your screen. So really, standard in and standard out, standard out and standard error are, in this picture, not actually connected to a screen at all, but rather they all go through the internet, and then that's connected to your screen, right? And then likewise over here, your keyboard is not directly connected to standard input. It goes through the internet and then is connected to standard input. Okay, but let's forget the whole internet part of it for now, because that just like adds a layer of complexity that isn't important for this picture. So this is the default setup for your program. When you type in a command on the command line, you can change where this is connected to. And you can change where this is connected to. And that's what that less than sign and greater than sign is for. So I could have a file over here, a file on disk. And using the less than sign, change where the input comes from. By default, it's your keyboard. But by using the less than sign, we switch it from the keyboard temporarily. We switch it from the keyboard to this file. And then the shell will open up the file and then send characters into standard input, which arrives in your program. And again, your program has no idea that the data is now coming from a file. It thinks that it's just somebody typing really fast on the keyboard. And likewise, we can use the greater than sign to redirect where standard out goes. That could also go to a different file. And again, your program has no idea that this is happening. It's just sending characters to standard output, and the shell redirects it into a file. So your program is just going along, doing its business, reading stuff from standard input, sending it to standard output. It has no idea what's going on beyond these lines over here. It has no idea that standard input is no longer connected to your keyboard, but is now connected to a file. And likewise, may have no idea that standard output is no longer connected to your screen, but is also connected to a different file. And now the output that would have gone to the screen is instead redirected, diverted, if you will, into a file where it appears. And the pipe symbol can be used to redirect either standard input or standard output, not from a file, but from another program. So you might have here a program sitting over here, I'll call it P, and another program over here, I'll call it P. Actually, this is just a whole separate diagram. So I'll just go to another screen. This is program 1, program 2. Each one of them, of course, has standard in, standard out, standard in, standard out. And so if I type on the command line, program number 1, pipe into program number 2, all the shell does is just run a connection between the standard out of program number 1 and the standard input of program number 2. And then that's all the pipe does, is it just connects up those two clouds, if you will. And then all data that program 1 generates goes to standard output. That finds its way over to standard input of program number 2, and then winds up in the input of program number 2. So the greater than and less than signs are used to redirect input and output to a file, and the pipe is used to redirect standard input and standard output to another program instead of a file. How do you like that explanation? And you can mix and match. You can redirect things separately. Like you could have the standard error of program number 1 go to a file, and the standard output be piped to another program. So you can do fancy stuff like, oh, by the way, in this picture over here, standard input is file number 0, standard out is file number 1, and standard error is file number 2. So they all have numbers associated with them. So I could do something like program 1, redirect errors into error.log, but pipe standard output into program number 2, which is also having its errors redirected into, let's say, /dev/null, which causes those error messages to just be flushed away so you never see them. So in this case, you've got standard error going into error log. And here you've got standard error being thrown into the rubbish bin. Not literally the one on your desktop, but like it's just simply, actually maybe not even the rubbish bin is not a good analogy here. It is a swirling black hole where data goes in and never comes out. All right, so in this command line here, program number one's standard error is going into a file so that all the error messages appear there, and its standard output is being piped into program number two, and program number two's error messages are just being thrown away. It's called /dev/null. It's the null device. It's a file that it's a special file on the system that you can write to. You can never read from it. If you attempt to read from it, you'll get nothing. So all data that's piped into that file or sent to that file just simply flushed away. And then the question here, the last question is, how do you, since these are files, can you basically close them? And yes, you can. You can close them like you would any other file, although since they're known by their file numbers, you're going to use the close function instead of fclose. So you can say close 0, which means close off standard input. So the program will accept no input whatsoever. If you attempt to redirect from a file or just connect it to your keyboard, nothing will happen. The data will just simply be discarded. You could close standard output, and then nothing will appear on the screen, or nothing will go to a file. However, once you close that file, once you close standard output, your program should not attempt to print anything because that would be an error. You're trying to send data to a file that's been closed. You can also use the fclose functions. You just have to use them by their names instead of their numbers. You can say fclose standard input and fclose standard output. So your program could actually internally do redirection. If you want your program to redirect all things that normally get printed, but instead to a file, you could do that yourself in your program. You just have to close standard output and then open it again to a new location. I'm curious now. We have a few minutes. Let's do something that's totally different. Let's call this, I don't know, I just need a throwaway name. Let's just call this April 7th. Right, just something for today. So let's have it print to the screen. All right, and you've seen this before. If I run it, it goes to the screen. My layout is off. I'm not sure what you mean by that. Anyway, let's move on here. So I'm not going to change this line here at all. I'm not going to change that. What I'm going to do is let's go fclose standard output. So now if I try to run that program, well, nothing appears, right? I'm thinking I should have gotten an error message because I'm attempting to write to a file that is closed, but apparently it doesn't. But let's go ahead and let's open that again. So we'll go, let's see, can I do this? Standard out equals fopen. And let's write to, what should I call this? Just call it output.txt. Let's open it for writing. And let's make sure we actually were able to open it. So if not standard out. I can't really do a printf, right? I can do a fprintf to standard error, right? Because I didn't close that. So I can still use my standard error to see error messages. Can't open standard out. Actually, I'll go ahead and just use, I'll just use p error because I'll want to see what the reason is. Can't open standard out, and then we'll exit the program immediately. All right. So it compiles. Now let's run it. Okay, so I've closed standard output and then opened it again using the same variable name, but I'm opening a different file called output.txt for writing, and then check to make sure I actually could open it. And then we'll just do our printf. Remember, printf by default is going to go to standard output, but now I've rediverted standard output to go to a file instead of the screen. And I'm doing this internally within my program. I could do it externally using the less than and greater than signs, but here's how it gets done internally. Right, nothing appeared. And then down here, here it is. There's the output. So it's really as simple as that. Standard out is just a file as far as your program is concerned. Go ahead and close it and open it again with a different file. And now everything that would have gone to the screen is now going to go to that file instead. This is a really cool way. I mean, other than doing shell redirection, which is really the easiest way to do it. But this is a really kind of a neat way where if you have a program that normally produces a lot of output to the screen and you instead want that to go to a file, all you have to do is just redirect where that file is. And then if you want to then print back out to the file again, you have to close standard output and reopen it with the file that it was before. I'm not sure what that file was. I think it's called /dev/tty, but I'm not entirely sure that that's what the name of the file was. I don't know. Let's try it. So we'll fclose standard out, and then we'll open it again. I think it's dev tty, and we'll open it for writing. And this should go to the screen. There we go. So that was correct. That's the name of the file that corresponds to your screen. And you're right, we just lost portability. So this is not necessarily going to run on a Windows system. This runs on a Linux system here. So if you want to make this be able to compile and run on different systems, then you'll have to have kind of like different versions for each operating system. So whenever you call printf, all that printf does is just call another function. Here's what printf would look like. If you know, it would look like this: void printf, you know, whatever the parameters are. But internally, it just calls fprintf, and then puts standard out as the first parameter. That's all that printf does, is it just calls fprintf and passes in the name of the file or the variable that points to the file you want to print to. Really, that's all it does. So fprintf just calls, printf just calls fprintf. And scanf just calls fscanf. Passing in standard input as its default. So by closing standard out and reopening it with a different file, when we call printf, it still calls fprintf was standard out, but now standard out is pointing to a different thing. So my program doesn't have to know at all that where standard out is going is now different. It just calls printf, which calls internally fprintf, and we've just switched out where it goes to. This is one of the really cool things about abstraction. You've heard that, hopefully heard that word before. Abstraction means to hide the details of how something works. So printf is an abstraction because it hides the fact that underneath it just calls fprintf with standard out as its first parameter. And then fprintf is itself an abstraction because it hides the details of how standard out actually works. As far as your program is concerned, it's just a file, an ordinary file to print to send data to. But behind the scenes, a lot of stuff is going on in order to connect that to your screen. But because of that abstraction, we can swap out what standard out does with something else. We can swap out the fact that it's connected to your screen with now it going to a file instead. And you know, instead of using fopen to open up a file, we could use popen to open up a pipe and send the output from that program into another program, and essentially accomplish the same thing that the command line does using the less than, greater than, and pipe symbols. You could write an app to instead write to /dev/SDA, which is the hard drive, and then that would overwrite the contents of the hard drive. And you're right. If we had access to write to that device, then we could do that, but we don't have access to that. As a normal user, we don't have access to that. If we were the root user, the system administrator user, then yes, absolutely. You could write to that file and completely corrupt your disk drive. So being the root user could conceivably, if you run the wrong programs, just completely corrupt your hard drives. So that's why you don't typically spend a whole lot of time as the root user. You go in, you become the root user, you do what you need to do, and then you get out. Become your unprivileged user so that you don't accidentally do things like this. It's really like, you know, if you have a fair amount of experience, it's really hard to do these sorts of things. You know, I have decades of experience as system administrators on Linux systems, and so I actually do spend a significant portion of my day as the root user. I'm just careful not to run commands that could potentially overwrite things like the hard drive. And again, it's not super common. I mean, you'd have to go out of your way to type in something like dev/SDA. It's not like that would just happen as a normal course of events. Well, wow. So we learned a whole bunch of new stuff today. Like we learned about standard in and standard output and its relationship to files on a Linux system, and the fact that you can change where the variable names standard in and standard out actually point to. So by default, it's connected to a file called /dev/tty, which is connected to your screen and keyboard. If you open it for reading, it'll get it from the keyboard, and if you open it for writing, it'll connect it to your screen. But then you can just close standard output or standard input and then get the data from somewhere else, essentially accomplishing within your C program what the shell does for you with the redirection characters. Oh, is it possible to type rm-rf/ by mistake? It absolutely is. As the root user and go through and just wipe out your entire hard drive. That's another story. I have done something like that on a production system that had like live users on it. Yes, absolutely. I have done that. Now that is a learning experience. How can you recover from that? without going to backups? That's an interesting one. Like, assuming you do have backups. What if you don't have backups? Can you recover from that? I mean, it depends upon how quickly you stop the process. If you can stop it early on, it might not wipe out so much stuff. If you wait too long, it starts wiping out more and more data, and then it's harder and harder to recover from that. I have a shirt that says sudo rm-rf, don't try this at tilde, which means don't try this at home. Yeah, I've got all sorts of stories about bumbling mistakes I made as a system administrator on live systems. Yeah, it happens. People make mistakes. The question really becomes, how can you avoid making those mistakes in the future? And if they do happen, not if they do happen, when they do happen, how quickly can you recover from it? That's something that these large organizations like Google and who else, like Microsoft, Apple, they actually have drills periodically where they have this is an actual job you can get at a place like Google. It's like the disaster recovery team or the disaster preparedness team. And what they do is they go to different functional units within Google. Like, let's say they go to the search people, the team that runs Google search. And they'll go in and do stuff like go to the data center and cut a cable, just a random cable. And then check to see what's the response time to that. How quickly do they notice that there's a problem, and how quickly do they fix it? Hopefully they've got processes in place to detect these things when they happen, and other processes in place to kind of route around the problem until someone can go and physically repair it. You know, so cutting cables is one thing you do. You could go in and you could, you know, just unplug one of the servers, and again, see it unplug, like remove the power, just pull the power, and see how, again, how quickly is that problem detected and routed around. Let's say you're running the email, they're running Gmail, and someone goes in and changes the IP address where mail is supposed to go to. So that could happen as just a misconfiguration. Again, how quickly is that problem discovered, and can it be routed around quickly? So there's actually teams of people in Google, that's their job, is to cause problems and then measure the response time. That sounds actually kind of like an interesting job, because you get to learn a lot about the different functional units, and you get to learn about how their processes work, and you get to help them prepare for problems that happen. Yeah, I think that would be a really cool job. So even if you don't work at an organization like that, if you do work at a smaller organization that is providing services to the public or services to a large customer base, think about that. Think about problems that could happen, and how could your team recover from those problems as quickly as possible. Let's say someone went in and just, again, like pulled the power on one of your servers, or cut a network cable, or deleted some critical files on your servers. How quickly could those problems be discovered, and how quickly can it be fixed? Again, if you work at a small organization or a medium-sized organization that doesn't formally have these processes in place, talk to your manager or talk to your, whoever you need to talk to, and say, like, I've been thinking about what would happen if this event were to occur. Maybe we're not so prepared for this to happen. What can we do so that we can improve the response time? And I think that if you can convince the management that this is a good idea, that really can set off a long chain of discussions about how can we actually execute these types of drills, but first of all, in a safe manner so that we don't affect production systems, so that we can just try things out and put the processes into place, and then work our ways towards actually trying them on production systems. So there was a suggestion here, is like maybe set up a development environment in virtual machines so that you can try these things out and then reset easily if problems happen. And then once you've got your processes in place, then try it out on the real production systems. See if it'll work. And again, you got to get buy-in from everyone that you're deliberately going to cause problems on the production systems. Maybe it means containerizing or putting into Docker all of your critical systems so that they can be restarted quickly. Maybe it means running virtual machines on your production systems so they can be restarted quickly. But again, what if the virtual hosts go down? What if the host systems go down? So your disaster preparedness team may also spend a lot of time thinking about what insidious ways can we cause problems? Like what little subtle ways can we introduce errors into the system? It's not just a matter of like pulling the plug on a server. It could be changing one character in a critical configuration file that makes the process behave a little bit differently. Not like a huge error that would cause it just to not start up. That would be obvious to find. But like just one little minor change somewhere. Maybe a number was changed that affects the behavior. So for organizations like Google and Microsoft and Apple, these are really important things to think about. And it does, I mean, it's not just about preparing for disasters, it's about just improving the product overall and getting organizational units to talk to each other about, if the problem happens over here, how does that affect other functional units? So if email went down, it may not just be your customers that are affected. It could be internal email is affected. And if that's the way you deliver information to other units, if that's the way that let's say, problems are conveyed to other units, and if the internal email goes down, do you have another way of sending that information? So talk about backup in terms of not having duplicate copies of things, but having is there a plan B in case plan A doesn't work? Oh, you're right. So this is essentially kind of like unit testing, where you're testing individual systems to see whether you can catch these problems early on. But it's also integration testing. If this system goes down, how does it affect these other systems? So it's kind of like API or unit testing, but on a larger scale. Anyway, I think that's enough for now. It's almost 12 o'clock here. It's starting to get warm. You feel the heat coming in through the window. All right, folks. I think we are done for today. I need to check something first. When are we getting to sockets programming? So after we do the password cracking, after we finish that entirely, then we're moving on to networking. So we're probably looking at, well, next week we have off. So the week after that, we'll do our final password cracking week, and then we'll get into networking very shortly after that. So we're probably looking at about 2 weeks from now to get into that. 2 to 3 weeks, somewhere in there. And then we'll spend about 2 weeks on that. Okay. Well, I hope you all have a great Easter break for students in my classes. For those of you who are not in my class, just watching on this YouTube, then I hope you all just have a great week off from watching these streams. If you want something to do, then go to one of these websites like Project Euler and just try solving some of the problems on there. It's just good practice for doing programming. Project Euler, Code Ninja, any one of those websites where they just give you a whole bunch of little problems to work on, and you just write a program to solve it. It's just good practice. All right, take care, everyone. I'll see you in about 12 days or so. All right, bye-bye. That was for my Zoom folks, and then the YouTube folks, same thing. I'll see you in about 12 days. Hope you all have a great week, and I'll talk to you later. Bye-bye.